We have discussed the DC-DC converter acting as a power interface between the PV source and R0 by impedance control, and we have also seen how the various MPPT algorithms operate. One of the practical points that I would like to mention at this point is housekeeping power supply. What is housekeeping power supply? It is actually the power supply that will be powering up this MPPT controller. Let me mark the power supply positive and the ground point like this. So this MPPT controller itself should have a power supply because it needs to power up a lot of components which are there within. You may use analog op-amps, analog circuits, in which case you will need for the VCC here plus minus 15 volts. So probably you may need VCC to be a single power supply, 15 volts, 0 to 15 volts. You may probably need a dual power supply of plus minus 15 volts, or if there are digital logic, then you may need plus minus 15 volts and a 5 volt supply. And nowadays microcontrollers and microprocessors have 3.3 volts, and therefore you may need a 3.3 volt. So like that, you, depending upon what components go into the MPPT controller, you will need specific power supplies that will power up the various components. Now the power supply that powers up this MPPT controller is called the housekeeping power supply. From where should it draw the power? Of course, it has to draw the power from the PV source only, because that is the only source available. And which is the correct point to draw the power and when. So that is what I just want to sensitize you on this practical point. Consider this PV source and the DC-DC power supply, which is acting as an interface between R0 and the PV source. You have a buffer capacitor CT, and across the buffer capacitor CT, let us tap off a line and let us draw the input for the power supply from here. So this will act as the input to the power supply circuit. So PS is the power supply circuit which will deliver some output. Now this PS power supply is itself a DC-DC converter. So normally you may have a non-isolated DC-DC converter for very low power applications, and you may have an isolated DC-DC converter topology for higher power applications. But in general, compared to this load power, the power drawn for this purpose will be very low. For power supply purpose will be low power. Note that this power supply output which I am showing here, which I will mark as VCC, need not be a single supply. It can be multiple supplies depending upon the requirements of the MPPT controller. Now this supply has to supply not only the MPPT controller circuits, it also has to supply any gate drive circuits for the power switches which are there within this DC-DC converter. So if I am having a power switch, an IGBT power switch, where the gate drive requirement needs an isolated gate to drain, gate to source drive, then in that case you need to have isolated supplies for that purpose also. So you may land up with isolated power supply in some cases, depending upon the placing of the switches here, depending upon the switch topology that you may use, and have a combination of isolated and non-isolated power supplies at the outputs here. This topology, where I am taking the power input from the terminals of the PV, is generally for low power, low voltage, for low voltage kind of an application. So in low voltage applications, this here may be around 16 volts to 40 volts open circuit, and therefore you may have around 12 volts under normal operating condition if it is a 16 volt open circuit, or it may be around 32 to 33 volts operating condition for a 40 volt type of module. So that can be directly converted through a power supply, and then the required output can be obtained by non-isolated DC-DC converters too. But in cases, in applications where the terminal voltage here is very large, let us say you are trying to put energy into the grid. In such a case, this voltage may be as high as 700 volts open circuit, and under operating conditions it may come down to 600 volts. So you may have a very high voltage here, and that needs to be converted to 5 volts, 3.3 volts. The step down ratio is very large, and non-isolated type of supplies will not give good solution. Therefore you may have to go in for an isolated topology. That in such a case, one may also consider taking from the output side if the output voltage is lower than the terminals of the PV source. So if the output voltage is lower, then you can probably you have a lower step down ratio to obtain the VCC, which will power up the microcontrollers and the MPPT controller boards, and also the gate drive circuit. But if you are taking from the output side, then there is one problem. At startup, there is no power for switching on the switches of the DC-DC converter, so no voltage will come to the output, so there is no power, housekeeping power supply. In turn, there is no power supply for the gate drive circuit, so the circuit will never start. How do we make it start in such cases? Let us draw the input to the power supply from the output side of the DC-DC converter. So this is a power supply, and then it provides an output. Now here across the PV source, what we will do is build a small shunt regulator. So I will provide a switch there. I have a resistance and a Zener regulator. Now I will boost the current by having a BJT operated in the linear region, and I will interface them in this fashion. I will put a diode here, and I will put a diode here also, and at the center point I will take out, so I will connect this here, and this will be the VCC. So how will this operate? So during the start, you will see that there is no power for the DC-DC converter. So therefore, the output of this power supply is also low. So what I will do, I will press this reset button. You press the reset button, there is voltage applied across this resistance Zener combination, and this will be at some potential. Now let us say I will keep this at 16 volts. Now 16 volts minus 0.7 will occur here, because this will now be in the linear region. 16 minus 0.7, 14.3, 14.3 minus another 0.7 will be 13.6. So 13.6 will appear across here. So this VCC will be used for generating the gate drive for switching this DC-DC converter. So the moment the switches of the DC-DC converter switches on, the output will start developing. Now that will be given as input to this power supply, and that will give the necessary output. Now that will be at 15 volts. Now that 15 volts minus this one 14.3, it will reverse bias this diode, and power will flow from this power supply into the micro controllers and the other components that make up the MPPT controller board, and also the gate drive for the DC-DC converter. So all you need is for this to be on for just few milliseconds, so that there is enough number of cycles, high frequency carrier cycles, that will build up the voltage for the DC-DC converter. So actually when you press and leave it, the human reaction time itself is around 10 milliseconds. There is more than sufficient number of high frequency cycles possible for the DC-DC converter to build up the voltage, which will build up this voltage and which will then start self-sustaining itself. So this is the startup circuit that one may use, because you are just using it for a fraction of our time with a very small duty cycle. This this portion, even though it is a linear regulator, will not consume much, because this is only used for startup, and then after this is released, this will not consume any power at all. So this is the trick that is done for starting up in case you take from the output side. Now when you take from this output side, this power supply can be any type of power supply, and most of the time this will be an isolated power supply which will have multiple windings here, and each of the windings has as I said specific loads that they need to supply. For example, the 3.3 volt will go to a microcontroller, the plus minus 15 volts will go to the op-amps type of circuits, and like that the power supplies here, each power supply winding will have a function. Now there will be one or two windings for gate drive. So let us say if there is one power semiconductor switch here with a floating source, then one of the windings will be used for gate drive of this particular semiconductor switch in the main DC-DC converter. So therefore housekeeping power supply design itself is very, very important, and one has to give a lot of thought to it. Most of this week we had discussed on the MPPT algorithm and the MPPT issues with respect to the DC-DC converter. I had not discussed anything on the design of the DC-DC converter, but there are a host of books and lot of literature available in the net, and also NPTEL lectures, switched mode DC-DC power conversion, NPTEL lectures by Professor Ramnarayanan and myself. They are also available, where a lot of information on DC-DC converter is given, where you can refer to them and try to design and get more insight with respect to the DC-DC converters. So now completing this power supply powers up this MPPT controller board, and along with this housekeeping power supply, this whole portion drawn in blue will form the housekeeping power supply, and that is needed for the MPPT controller board to work properly. One important point to be noted with respect to the MPPT controller is that by putting this power supply and the startup power supply to power up this, there is some power which is consumed by this MPPT controller board, and also the gate drive for the DC-DC converters. Should note that this power supply itself acts as an additional load, either here or when you put it here, it acts as an additional load. There will not be any change in the function of the MPPT controller, because it is sensing the IT and VT at the terminals and the current flowing through the PV panel, and therefore the power that is delivered from the PV source also contains the power that is needed by the power supply to supply the MPPT controller. So therefore, operation wise, there is no issues with the MPPT controller. By introducing this power supply, it will still be tracking to the peak power point. However, I would like to at this point mention 2 points. One is the power supply circuit, the housekeeping power supply circuit should not consume more power than what is being delivered to R0, because then it is not meaningful. That is one point that you have to keep in mind. The cost of this power supply and all this MPPT controller algorithm should not be prohibitively high. It should not be much higher than your main DC-DC converter and R0. So then again, it is not meaningful to have a MPPT tracker. So it makes sense to have a maximum power point tracker only if the cost of this MPPT controller and the associated housekeeping power supply is much lesser than the main power and the load, and the loss in power to this housekeeping power supply and the MPPT controller should be very low compared to the amount of power that is to be delivered to R0. So these two things you keep in mind before deciding whether MPPT is really required or not for that particular application.